Hi everyone. Today we are going to do possibly one of the most complex optimization examples I have in my deck. My name is Christian and I will be walking you through today's tutorial. Here is an overview of the structure we are going to optimize. At the base, you can see that it's pinned. At the top, we are going to have multiple load cases that apply the loads in different combinations. Our goal by the end of the video is to optimize the dimensions of the structural members such that we minimize the weight as much as possible. You'll see that the weight is actually increased by the end of the optimization. The reason being is because some of these members are already experiencing failure. Some of our stress and buckling constraints are already being violated. When the optimizer sees this, it's going to first try to satisfy those constraints, and then it will worry about minimizing the objective afterwards. So that's why you see that you see the weight actually increase, and that happens because it's trying to satisfy the constraints. Now, this is what I plan on covering. This possibly will be a very lengthy video. So the first thing I want to cover are some details regarding the structural model. After that, I want to go over something very critical, which is the optimization problem statement. This is basically a summary of your variables, your objective, and your constraints. Then I get to walk you through each step you need to take to set this up to run in Nastran Solution 200. We'll go ahead and perform the optimization, and then towards the end, we'll go ahead and look at the results, and then we'll update our original model with the optimized structural dimensions. Now, just in case you are a professional engineer and you would like more training, if you have a complex question regarding Nastran Solution 200, you're welcome to contact me at this email address and I will definitely get back to you. Now, today we are going to use a special Nastran Solution 200 web app. This is actually what enables us to perform optimization. This is available to both students and engineers. So if you're interested in using this, you can also contact me at this email address. Now, this example can be found in the Nastran Design Sensitivity and Optimization User's Guide in Chapter 8. This example is called the 25-bar truss example. I definitely refer you to this document if you want to understand every detail of this example. So now moving on, let's talk about our optimization problem statement. If you look back on the previous slide, we are using one-dimensional elements. One thing to keep in mind with these one-dimensional elements, the cross-section, if you will, is not explicitly defined with dimensions of a cross-section. For example, if this was a square cross-section, we're not defining, the cross-section with a width and height. If it's a circular cross-section, we're not explicitly defining the radius of this cross-section. What we are doing instead, we are just saying that this cross-section has some area, A. Now, this is sort of tricky for us because we want to vary, say, the diameter, or rather, let's assume that the area or the cross-section of the members is circular, and we want to vary the area in terms of diameter. So here, what we are going to do is define a relationship between the area, and the reason is because the area is the actual property of the element. We are going to define a new design variable called y1 that will represent the raw diameter. We are then going to express the area in terms of this raw diameter with this given expression. There happen to be 8 different types of areas in this the structure. It's not visible here. Let me see if I can find a better image for you. This is possibly the better image here. So everything in red has its own area. Everything in yellow has its own area specified. The green ones have their own area specified. If you count each different color, you'll see that there are 8 different types of areas that are being used in the structure. So that's why you see on the next slide, we are going to define 8 different design variables that correspond to the respective rod diameters. And then we are going to associate it to the area using these given expressions that you see here on the right. One other thing, we want the design variables to arrive at specific values. We want the rod diameters to land on values such as 0.1, 0.5, 1, 2, all the way to 100. If we arrive at a value like 1.69, that is not a value. We want the value to either be 1 or 2.0. Now, we just went over the design variables that we just defined. One other thing to note, we already know what the areas of the members are, so we have to back calculate what the rod diameter would be. Here I've calculated that it's 2.52, so if you plug in 2.52 into this first expression, you'll get the area of P rod 1. So P rod 1 would be this reddish section. So here if you plug in 2.52 into this expression, you'll get the area that was used in the finite element model. We are going to let the range of values vary between 0.01 and 100. What else are we going to do? Let's talk about the objective and the constraints on the right hand side of the screen. This finite element model is going to generate a lot of outputs or responses. You're going to have displacements at each node. You're going to have strains and stresses for each element. Now, this is the part where you pick out of all of those responses what you want to minimize or maximize for your objective and what you want to constrain. For our objective, we are going to say that we want to minimize the weight. For our constraints, there are quite a number of constraints in this example. The first one being axial stresses in the elements. We are going to take each element and make sure that the axial stress is within negative 40,000 and 40,000 units of stress. One other thing, we are going to have displacement constraints at grid or node 1 and grid 2. So these would be the nodes that are circled in red here. We are going to say that the x and y displacement of those nodes should be within negative 0.35 and positive 0.35 units of displacement. One other thing we want to consider buckling. Since this is a static analysis, we are going to have to come up with an equation that's going to tell us if the members are exceeding some buckling scale. So here is that expression that will tell us if the member is buckling or not. You can see it's in terms of L, which is the length of the member, the Young's modulus, the diameter of the cross section, if you will. And one very important value is the axial stress, sigma. So your sigma here. So we are going to program custom constraint equations that are going to consume the axial stresses. So here you can imagine this R1 is going to be fed into this equation along with the length of the member, the Young's modulus, and the rod diameter, which is represented by the design variable Y1. Then we're going to get the buckling value for this specific member, if you will. And then we are going to say as long as the buckling factor or buckling number is less than 1, the constraint is satisfied. One thing to keep note regarding these equation constraints, there are multiple ways of writing the same equation. Here you can see that the equation is written in one equation. Nastran has alternative methods of typing in your equation. You can type your equation as a series of equations. For example, here we can type in this first equation into Nastran. G is then used in a subsequent equation. So here you can see me go down to the third equation. This next equation takes on the value of G2, and then in it takes the value of G2. This G2 then cascades to the next equation. So first you define G and G2. Any following equation can use those previously created G and G2. So by the end, we have G3, which is the same value as this equation that you see here on the screen. And here is just a third example of how you can write the same expression. So here we define G here. Once G is defined, it can be used in any subsequent equation. So here we use G in the next equation, and then G2 is giving us our buckling value. And remember, this should always be less than 1.00, which means that you are precluding buckling. Now here I just have a table that's telling me what the parameters are for each variable in the equation. So here we have the length, we have the design variable R1. So I'm going to define 8 equations throughout this tutorial. So here, let me just review this. Also, remember earlier I said that there are multiple load cases. We are going to apply all of those constraints to both load case 1 and load case 2. Now here is just a big snapshot of the optimization problem statement. Remember, this is composed of 3 things. The first one being the design variables, the next one being the objective, and the third component being the constraints. It's always important to have this drafted before you ever start your Nastran procedure. Now let's go over the steps that you need to take in order to set this up for Nastran. Number 1, you should have a BDF file all ready to go. Here I've already gone ahead and constructed this BDF file in a pre-post processor. Here you can see my structures here. When you perform your analysis, you get a BDF file that's been created for you. This BDF file has the entire structure. It has the loads, the materials, the position of each element and node. This file now has to be converted to Nastran Solution 200. If you are following along with this tutorial, you can download this file by going to the user's guide, and then in the tutorials section, specifically the size optimization tutorials, if you scroll down until you find optimizing for buckling, the starting BDF file is available here. So right click on this link, save the link as, and in a moment you'll find that the file is now available on your desktop. So this is our starting point, the BDF file. We are going to upload it to the Nastran Solution 200 web app in a moment. This is going to let us convert the BDF file to Solution 200. We will specify our variables, our objective, and our constraints. Basically, we're going to express our optimization problem statement in the web app. Once we do that, we can perform the optimization with Nastran. We'll go ahead and look at the results very briefly. And then at the end of the video, I'll walk you through the process of how to update your original model with the optimized structural parameters. Now, let's go ahead and get started. Number 1, you need access to the web app. If you're a student or engineer, you can contact me at this email address at the bottom of the screen, and I will be more than glad to grant you access. This web app is what makes it possible to take an existing BDF file and convert it to Solution 200. Now let's go ahead and start the procedure. So let me go back to the main homepage of the web app, and let's click on size optimization. We'll go ahead and select the BDF file that we have. Remember, this BDF file contains the entire structural model. You notice that as we look through the long list of properties that can be set as design variables, there is no dimension for radius. There's no dimension for height or width of the cross section of the members. All we have are areas. But we want to define these areas in terms of rod diameter. So in order to construct that expression that I mentioned earlier, Here, let's go back to the optimization problem statement. I want to express the area in terms of the rod diameter using this equation that you see here on the screen. So how do you do that in the web app? Click on the options, and this will show you a new table. If you mark the checkbox for dvxrel2, this adds a new column to this table below. Once you click on, say, one of these plus icons, it moves the property down to this table, adjust dvxrel2. This is where you can type in your equation 3.14 times y1 squared divided by 10.0. So we have just defined a new design variable called y1 multiplied by pi, y1 squared divided by 10. So that completes the creation of this relationship where we say the radius, or rather the diameter, is related to the area by this expression. So the optimizer will vary y1, which in turn will vary a. Now here, this is where I have to specify the initial starting value of the variable. So here I'll go ahead and type in 2.52. Let's go ahead and make sure we use the correct balance for this. So 0.01 and 100, 0.01 and 100. And there we go. And the other thing you want to do, remember, we want the diameters to take specific values, 0.1, 0.5, 1, 2, all the way to 100. What you can do is just type in those values here, 0.1. Oh, I forgot the number already. Let's go ahead and look at that. 0.5, 1, 2.0. Instead of typing all these numbers one by one, what you can do is use the through and by method. So here I'm saying generate a string of values between 3 and 100. So 3 through 100, comma, by increments of 1.0. So this will generate the string of values that we need, 0.1, 0.5, 1, 2, and then 3 through 100 in increments of 1. So 3, 4, 5, ... all the way to 100. Now let's go ahead and repeat this entire process for the other ones. Instead of having to click each icon one by one, you can type in the expression here. So let's go ahead and do that. 3.14 times y2 squared divided by 10.0. And we'll go ahead and click on this bulk create icon or button. This will automatically click each plus icon for the dvxrel2 column. But remember, each area has its own diameter that will be varied. So we have to change all of these. The area here, the third row, should be y3, y4, y5, y6, 7, and 8. You can see as we create these new y design variables, they're automatically generated in the following tables. So now I have y2 through y8. This is the part where you simply just copy over all of these lower and upper bounds, just like we did for the first design variable. So again, the elements in our finite element model, they don't have explicit cross-section defined. Instead, they have parameters such as areas explicitly defined. But in our optimization problem statement, we want to vary the areas in terms of diameters for the cross-section. So that's why we use these specific expressions. When we use these specific expressions, we then generate these new design variables for the diameters. Now let me review my work real quick, just to make sure everything has been created properly. And now let's go ahead and move on to the next step. So that completes the creation of the left-hand side of our optimization problem statement. So this side on the left is completely done. Let's now focus on the right side of the screen. So the objective, we want to minimize the weight. This is usually the easiest part. So we'll go ahead and move over to the objective section. We'll look for the weight and we'll click on the plus icon. And here we have that this weight corresponds to label R0 and we want to minimize this weight. Let's move on to the constraints. Remember that we want to express, or rather we want to constrain the axial stress for each element. One thing to keep in mind, and it'd probably be worth showing you here. Let's go ahead and segment these properties. What I want to do right now is color coordinate the different members so it's a little bit more clear for us. And we'll go ahead and give this a new color here. Here we go. So here you can see that one property, say in white, is being used by 1, 2, 3, and 4 elements. We need to constrain each element's axial stress. So how do we do that in the web app? Once you're in the constraint section, filter the list. You can look through it page by page. You can extend the list. It's really up to you. Additionally, you can filter the list. We'll go ahead and click on the stress response one time. So here we have set a stress as a constraint, but now we have to specify which elements are going to be constrained. So here I want to say constrain any element associated with prod 1. And I specifically want to constrain the axial stress. Here you can see things like torsional stress also available, but in this case we want the axial stress. And I want the stress to vary between negative 40,000 and positive 40,000. So here what I'm saying is if there were 5 elements associated with prod 1, then those 5 elements would have the axial stress associated with it. Now, it's very important to pay close attention to what I just said. Let's go ahead and pull out our pen. So for example, the green elements, which is associated to prod 2. prod 2 has 4 elements associated with it. So when I create the next stress constraint with the label R2, this is actually creating 1, 2, 3, and 4 axial stresses, 1 for each element. So even though I define 1 constraint, in the background it's constraining 4 elements that are associated with the green prod 2 section. So let's go ahead and program that right now. So we'll repeat the process. We'll go ahead and say prod, axial stress, any element associated with prod 2. And then we'll go ahead and specify the bounds here. Keep note of these status markers. If at any time they are red, that means you're not complete with your optimization problem statement. You'll also get a warning about this when you go to the exporter. Here it's say, I know you want to export this design model, but you have an error that should be resolved. You'll most likely encounter an error if you ignore this message. So definitely keep this message, these error messages in mind as you go through this. So now let's see, where was I at? Everything looks good here. So let's repeat the process for each other prod. So I want 8 stress constraints in total. So this will all be applied to any element associated with the prod property type. And we'll go ahead and say this is for any element associated with prod 3, 4, 5, 6, 7, and 8. I want the axial stress constraint. And then in a moment, we'll go ahead and repeat the process for the lower and upper bounds. Now, after this, we are going to specify the buckling equation constraints that I mentioned earlier. Just in case you have any questions regarding the content of this video, feel free to send me an email, and I'll definitely get back to you with a response. One other thing, we want to constrain the x and y component of displacement for nodes 1 and 2 between negative 0.35 and positive 0.35. So to do this, let's go ahead and filter the table and look for the displacement row. We'll go ahead and select this response. And now here in the 9th row, we can say constrain both the T1 and T2 components, or the x and y components. So here it's a 1 and 2. We want this for grid 1, comma, grid 2. So nodes 1 and 2. And we want the displacement to be within negative 0.35 and positive 0.35. And now that completes the creation of the general constraints. Now we can create our equation constraints. So let's go ahead and focus on how to do that. Remember, there are multiple ways of writing these buckling expressions. So let me get my notes here so we don't have to look back and forth with the PowerPoint. So the first method of writing the expression will be in one entire equation. So here, let me look at this just to make sure this is correct before I start typing in data to the web app. And let me look at the second expression. R2, 130, 3.141, G1, and G2. Okay, so I think it probably would be best if I move this to the side. And then if I move the web app to the left also, that would be helpful. So now what do? This section is divided in two sections, if you will. Section 1, if you will, has predefined constraints that you can set. The second section, which is the bottom section, this section is where you can create your equation constraints. So here, let's zoom back in. And let's go ahead and click on this Create Equation Constraint button. This creates the constraint for you. This is where you can then specify the equation. So here, remember, we want to type in this entire expression all in one go. So 1.25 times negative 7.69 times R1. R1 is associated to this axial stress, so that would be the first row. Now you might be asking, what if there are 5 elements associated with R1? The equation constraint will see that there are 5 axial stresses associated with R1. It will plug in each axial stress into this equation, so then it will compute 5 R1 values. I'll repeat this again in a few moments. So let me go ahead and type in the rest of this expression. 3.14 squared times 1.0 E7 times Y1 squared. So let's go ahead and inspect this equation to make sure it's correct. We have for the numerator, negative 7.69 times R1 times 75 squared divided by 3.14 squared times 1.0 E7 times Y1 squared. Now let's go ahead and move this and ensure that the upper bound is set to 1. Remember, anything less than 1 means that buckling is not occurring. If it's greater than 1, then you have buckling. Now let's go ahead and create a second equation constraint. We're going to use this other method of defining the equation constraint. Negative 7.69 times R2 times 130.5 squared semicolon. So this first expression is automatically set to equal G. Although you don't see it here, if you look in the right hand side of the web app, this is where you can see the expression. G in terms of R2 is equal to negative 7.69 times R2 times 138.5 times 2. So know that G is there. It's just not immediately visible. After that, we'll go ahead and define our second expression for G2. So here we'll go ahead and type in G2 is equal to 3.14 squared times 1.0 E7 times Y2 squared semicolon. So now G2 is equal to this entire expression. You'll notice that we are using semicolons to separate our expressions. Finally, we say that G3 is equal to 1.25 times G divided by G2. Here, this is the last expression, so you can include a semicolon or you can leave it out. This last expression is what will be used to represent R2. Everything was essentially scratch paper, if you will. Here we define G, we define G2. We then use both G and G2 in the final expression. G3 is then used to represent R2. And now let me go ahead and zoom out and repeat this process using the third method of creating your equations. So here I have this table that we're going to need access to. So let me zoom out so it's visible. So this is the third method of writing the expression. Here I found this method the most convenient method for myself. You might have another method that you prefer, and this is why I wanted to show you all these different methods so you can decide which one you might want. So here, let me go ahead and order these by label. And here, you'll notice that there's still a red status for this R2, and that's because I forgot the upper bound. So let's go ahead and fix that to begin with. Now this first expression is quite complex, but we'll go ahead and grind through this. 1.25 times negative 7.69 divided by 3.14 squared times 1.0e7 semicolon g2 is equal to g times r3 times 106.8 squared divided by y3 squared. So here it's telling me that there is an error with one of these numbers. Let's go ahead and see if we can spot what exactly is going on. Oh, here it is. Exponents should always have the decimal point left out. Here I accidentally typed in an 8 instead of an asterisk, and that's why we had the error. Here what I'll do is that completes R3, so I'll just copy this equation for the other ones. So here this variable should be y4, y5, y6, y7, y8. This should be R4, the axial stress for P-rod 5, 6, 7, and 8. And now the lengths. Those will vary, so we need to take that into account. So here we started off with 75, 130, 106.8, 75 here. And then the next one's also 75. The next one's 181.4. 0.14 rather. The same for the next one, and then the last one's 133.46. And let me make sure everything is okay there. Now here, just give me a moment while I look at my notes and make sure that everything's been typed in properly. 1.25 negative 7.69 pi times the Young's modulus, g times the axial stress times the length of the member divided by the design variable at the end. So everything looks good. Let's go ahead and zoom out a little. And now let's go to the exporter, because this is where we can look if we are ready to export. You'll notice that we have this message, not all constraints have been assigned to a subcase. Let's jump there and see what has happened. This is where we have to assign the constraints to, the load cases. Nastran calls load cases subcases, so let's go ahead and do that now. We'll first mark all these visible checkboxes. You notice that axial stresses R3, 4, 5, 6, 7, 8, 9, those have all been assigned to a load case. Here we want to do the same for the buckling equations. So here, let's go ahead and move those to the other ones. So let's go ahead and disable these. If you hold the shift key and hover over the checkboxes, you can also mark them. The reason you want to apply this equation, buckling constraint, to an actual load case is because each load case will have its own buckling value, if you will. Usually, or rather, I'll spare us the discussion before it gets a little too confusing. Let me go ahead and make sure all these checkboxes are marked actually. So here, I think we are ready to go. You'll notice that the message disappears, so I am ready to perform the optimization. Let's go ahead and click on option 1 to download this new package. We'll extract this package, and then we will double click the desktop icon, start MSC Nastran. This is going to start the optimization for us. The web app is going to get updates regarding where the optimization is at, so we'll let that do its thing. Let's go ahead and look at some of the files in this directory. The model. This is the same original model that we had at the beginning of this tutorial. So this model that contains the entire structure has been updated. Before, it was a solution 101 file, but now it's been converted to solution 200. The other thing, there's a second BDF file, the design model. This includes all your statements for the design variables, the objective, and all the constraints that we specified earlier in the tutorial. So the optimization is complete. This happens automatically. The web app will load the results for you. It's always important to read the final message. Make sure that these green checkboxes are there because they indicate that you had a successful optimization. If you see a red X, that means there's an error in the optimization that should be looked at carefully. Here we see that at the beginning, we started at a weight of 660 units of weight, but at the very end, we landed at 800 units of weight. Remember that we want the design variables to land on specific values. So let's scroll down and look at those design variables. Here you see the optimization happen, but right before the last design cycle, it performs this procedure to land on specific values. For example, the design variable, which is the diameter of PROT7, the diameter or the optimal diameter is 3.286. But since we want to land on numbers in increments of 1, it moved the number to 4. It did the same for all these other elements where now we have values of 3, 2, and 0.5. And you see how there's a sudden jump in the design variables. You also see the sudden jump in the last design cycle. You go from 800 units of weight to 1008 units of weight. One last thing I want to mention here, the design cycle number. You'll see that we have 8, 9, all the way to 15, and then the last design cycle has 15D. The D means for discrete. This is the last step where it performs the procedure where it moves the 3.2 to 4, it moves all these other values to 3, and so on and so on. So that's the procedure where it lands on those specific values. So this first message means that you have convergence. So here you can see it's starting to level out, convergence. And then the second message, end hard feasible discrete design obtained. That means that when it moved from 800 to 1008.5 units of weight, this step was successful. There are situations where this is not successful. This happens in the following plot. Here we have a list of normalized constraints. Any normalized constraint less than 0.003 means you're violating, or rather you're satisfying a constraint. If the normalized constraint is greater than 0.003, that means you're violating a constraint. So here you can see we are definitely violating at least one constraint. This happens until design cycle 2. So here you see it's still positive, so we're still failing. Here we finally have values close to 0. So this is where we're starting to satisfy our constraints. By the end, when it performs that discrete design cycle, we now have a negative normalized constraint, which again, anything less than 0.003 means you're satisfying your constraints. So here we know that since we ended up at a negative normalized constraint value, we have obtained a feasible design at the end. So that's what that message means. Let's say one other thing. You might look at this and say, I defined a lot of constraints here. I defined R1 through R9. I defined all these buckling equation constraints, R1 through R8. How do I know which constraint this 1.82 is? How do I know what constraint this 0.32 is? And so on and so on. There's one way to determine this. If you go to the results section and click on responses F06, you can navigate to that folder and select the F06 file. And here you get a long list of values. When you load this, click on maximum constraint for each design cycle. So here, let's go ahead and move this to the left. And then I'll move the plot to the right. So here on the right, we see that the first normalized constraint is 1.827. If I look back in the responses table, I see that the first initial row here, the bolden normalized constraint is 1.827. This is corresponding to one of the buckling equations. Here, let me see if there's any additional data. Here you can see that the 3.3, this is the next one, 0.32997. Here, 2.015 e to negative 4, that's also here. So you see each row that we see here is now corresponding to each normalized constraint on the plot. So design cycle 1, 2, 3, 4, 5. Those are all listed here, 1, 2, 3, 4, 5, and so on and so on. So here I can say that for the initial design, the equation buckling, or rather the equation constraint for buckling of R7, so that would be, let's see if I can move back. So that would be this expression. This is the one that's currently dominating that design cycle. For the next one, it then moves. R3 is now dominating that design cycle. So that would be this expression here. And here you can see that after that, it then becomes R7 that starts dominating each other design cycle. And then by the end, it's R2. So that would be this expression that's dominating that last design cycle. So now that is the last point I wanted to make regarding the results. Let's go ahead and start wrapping this tutorial up. So here, as promised, we saw that our goal was to minimize the weight, but since we had the constraints being violated initially, some of the members had to be sized appropriately to make sure that we are satisfying both the stress and buckling limits. While that was happening, it actually caused the weight to increase. So this is a good example where you see that we start with violated stress and buckling constraints. The optimizer will size the members accordingly to the point where we are satisfying the constraints. And at the same time, it will either minimize or maximize the weight, like in this example. So now the last thing I want to leave you off with, if you notice that this PDF file has old areas for the properties. Here you see the original areas are 2 for 1 through 8. We need to update these areas so they use the new areas that we defined during our optimization. So for this, let's go ahead and copy this file and call this one updated. So here underscore updated, and we'll go ahead and open this file, close the others. In the directory where the optimization was performed, there's a PCH file. This PCH file has the updated properties that we can use. So here, let's go ahead and do this. So here on the right, which is the PDF we are updating, we'll go ahead and delete the old PRODs 1 through 8. So those are gone. Here on the left, we'll simply first notice that the areas are no longer 2. They are different areas. These are the areas that were computed. I don't have the window anymore, but these are the areas based on the new diameters, if you will, Y1, Y2, Y3, and so on and so on. So here, I'll go ahead and simply select all of these PRODs, and I'll paste them here on the right. I'll close the file on the left, and then I'll save this new file. And this new file here now has the updated areas that were obtained during the optimization. So that's the last thing I wanted to leave you off with. Quick reminder before we close, if you're a professional engineer and you have specific questions regarding this example, you can contact me at this address. If you want some more advanced training or if you want some personal guidance, I'm also available for you at this email address. If you are a student or professional engineer and you would like access to the web app, you can also contact me and I will definitely work on getting you access. With that, I'll leave it there and thank you so much for watching.